Hello, and welcome back to the Nocturnal Astronomer. I'm your host, Atlas Reed, and tonight we're embarking on one of the most serene journeys through the cosmos you can imagine. Picture an invisible highway system stretching across billions of light years, connecting every galaxy in existence like a vast neural network pulsing through the darkness of space. This is the cosmic web, and tonight we'll drift along its gossamer threads of dark matter. We'll explore filaments made primarily of mysterious dark matter that comprises 85% of all matter in the universe, forming the scaffolding upon which cosmic architecture builds itself. We'll float along pathways that funnel fresh gas into galaxies, encounter junctions where filaments meet creating massive galaxy clusters, and drift through vast cosmic voids where matter is so sparse it resembles an ocean with only scattered islands. If you find yourself drawn into tonight's peaceful exploration of these cosmic pathways, I'd love for you to give this video a thumbs up and consider subscribing to the Nocturnal Astronomer. We're building a community of fellow cosmic wanderers who appreciate the gentle mysteries of the universe. And I'm curious, what do you imagine it would feel like to actually travel along one of these dark matter filaments? Would it be like floating down a river of starlight, or drifting through cosmic mist? Let me know in the comments. Your poetic interpretations always inspire future journeys. Let's dive in. To understand the cosmic web, we must first travel back to when the universe was merely 380,000 years old, a cosmic infant by today's standards. At this moment, known as recombination, the universe had cooled enough for the first atoms to form, creating what astronomers call the cosmic microwave background. But hidden within this seemingly smooth afterglow were tiny temperature variations, quantum fluctuations from the Big Bang that would eventually grow into the largest structures we observe today. Think of these early fluctuations like seeds scattered across a vast cosmic garden. Each seed represented a slightly denser region of matter, primarily dark matter, that would begin attracting more material through gravitational pull. Over millions of years, these seeds grew, drawing in surrounding matter like cosmic vacuum cleaners, creating an increasingly complex network of filaments and nodes that would define the universe's architecture for billions of years to come. The cosmic web emerges naturally from the interplay between dark matter's gravitational attraction and the universe's expansion. Over these tens of millions of years, the dark matter assembled into a complex network of intersecting filaments called the cosmic web. Picture how soap bubbles form when you blow them through a bubble wand, creating thin films that connect at various junctions while leaving empty spaces between them. The cosmic web forms similarly, with matter flowing along preferred paths while leaving vast voids relatively empty. These massive, thread-like formations can commonly reach 50 to 80 megaparsecs, with the largest found to date being Kipu, at 400 megaparsecs, stretching distances that dwarf even our local group of galaxies. To visualize this scale, imagine the Milky Way as a grain of sand. A typical cosmic filament would stretch from New York to Los Angeles, while the largest known filament, Kipu, would span from Earth to the Moon and back again 16 times. What makes these filaments particularly fascinating is their composition. Dark matter's dominance over everyday matter also means it dominates the filaments of the cosmic web, forming an invisible scaffold along which the universe's structure takes shape. Dark matter, that mysterious substance that doesn't interact with light but comprises most of the universe's mass, creates the invisible highways that guide normal matter, the kind that makes up stars, planets, and ourselves, along predetermined paths. The formation process resembles how rivers carve valleys through landscapes over geological time. Just as water naturally flows along paths of least resistance, creating networks of tributaries and main channels, matter in the early universe followed the gravitational landscape created by dark matter. flowing along filaments toward the deepest gravitational wells that would become galaxy clusters. These pathways don't exist in isolation. These filaments and sheets are separated by cosmic voids, vast empty regions that contain very little matter. The relationship between filaments and voids is symbiotic, each defining the other. Filaments exist because matter has been drained from the voids, while voids exist because their matter has flowed into the surrounding filaments. Computer simulations reveal the web's intricate beauty. When astronomers modeled the universe's evolution using supercomputers, dark matter clumped into blobs along narrow filaments with superclusters of galaxies forming a cosmic web at scales on which entire galaxies appear like tiny particles. These simulations show a universe that looks remarkably similar to neural networks and biological systems, suggesting fundamental organizational principles that operate across vastly different scales. The cosmic web's influence extends far beyond its role as cosmic architecture. It actively shapes galaxy formation and evolution, determining where star formation occurs and how galaxies interact with their environment. Galaxies born along filaments experience different evolutionary paths than those in voids, receiving steady streams of fresh gas that fuel continued star formation like cosmic feeding tubes. As we drift through our minds along these invisible highways tonight, consider how the cosmic web represents the universe's attempt to organize itself. From quantum chaos comes cosmic order. From microscopic fluctuations emerge structures visible across billions of light years. The filaments we're exploring represent nothing less than the universe's skeletal system, the hidden framework that supports everything we can see and touch. Mapping something invisible presents unique challenges, like trying to chart ocean currents by watching floating debris or detecting wind patterns by observing how leaves dance through the air. The cosmic web, composed primarily of dark matter that neither emits nor absorbs light, requires similarly indirect methods of detection. Astronomers have become cosmic detectives, piecing together evidence from multiple sources to reveal the universe's hidden scaffold. The most obvious clues come from galaxies themselves. Each bright knot is an entire galaxy, while the purple filaments show where material exists between the galaxies. To the human eye, only the galaxies would be visible, and this visualization allows us to see the strands of material connecting the galaxies and forming the cosmic web. When astronomers map galaxy positions across vast regions of space, they discover that galaxies aren't randomly scattered like stars across Earth's night sky. Instead, they form chains and clusters connected by seemingly empty regions, outlining the underlying dark matter structure like Christmas lights strung along invisible wires. Large-scale galaxy surveys have revolutionized our understanding of cosmic structure. Projects that map millions of galaxies reveal a network of filamentary structures that are analogous to the cosmic web seen in numerical simulations. These surveys show that galaxies trace out the same web-like patterns that computer simulations predict, providing strong evidence that our theoretical understanding matches cosmic reality. But galaxies represent only the tip of the iceberg. The real breakthrough came when astronomers learned to detect the gravitational effects of dark matter filaments. Just as a massive object bends the fabric of space-time, causing light to curve around it, dark matter filaments create subtle gravitational lensing effects that distort the shapes of background galaxies. Think of looking through a bathroom window with textured glass, where the imperfections slightly bend and distort the view beyond. Dark matter filaments create similar distortions, though much more subtle, that require sophisticated analysis to detect. Recent technological advances have enabled direct observations of filament material. After hundreds of hours of observations, an international team of researchers has captured the sharpest ever image of one of these cosmic filaments. These breakthrough observations reveal not just the dark matter scaffold, but also the normal matter, primarily hydrogen gas, that flows along these cosmic highways. Scientists have also discovered ways to detect dark matter filaments using gravitational effects on surrounding galaxies. These are filaments that sit isolated between galaxies and the largest and most hidden portions of the cosmic web. Advanced telescopes and analysis techniques now allow astronomers to measure how the gravity of these invisible structures affects the motion and distribution of nearby galaxies, much like detecting an underground river by observing how surface vegetation grows in patterns above it. The cosmic web reveals itself through temperature signatures as well. Gas flowing along filaments heats up due to compression and gravitational interactions, creating detectable X-ray emissions. Space-based X-ray telescopes can sometimes spot these hot gas trails, revealing the pathways that normal matter follows as it flows along dark matter filaments toward galaxy clusters. Radio telescopes contribute another piece of the puzzle. Astronomers think that cold, dark filaments in deep space snake their way to the galaxies, supplying them with gas, which is fuel for making more stars. Radio observations can detect hydrogen gas in these cold filaments, revealing the fuel supply lines that keep galaxies actively forming new stars. Computer simulations play a crucial role in cosmic web detection. Astronomers create detailed models of how the universe should evolve from initial quantum fluctuations to the present day, then compare these predictions with actual observations. The size of the simulation is a cube with a side length of 134 megaparsecs, or 437 million light-years, allowing researchers to model cosmic web formation across vast scales and verify their theoretical understanding. The most remarkable aspect of cosmic web detection is how multiple independent methods all point to the same underlying structure. Galaxy surveys, gravitational lensing, X-ray observations, radio telescope data, and computer simulations all reveal consistent patterns, like different instruments in an orchestra playing the same cosmic symphony. This convergence of evidence gives astronomers confidence that their maps of the cosmic web accurately reflect the universe's hidden architecture. As we continue our journey along these invisible highways, we begin to appreciate how human ingenuity can reveal the universe's most hidden secrets through careful observation, clever analysis, and patient detective work spanning decades of research. Imagine cosmic rivers flowing through the darkness of space, carrying the raw materials that fuel star formation in galaxies throughout the universe. These aren't rivers of water, but streams of hydrogen gas flowing along dark matter filaments like nutrients through cosmic arteries. Tonight we'll follow these celestial waterways as they deliver the essential ingredients for stellar birth to galactic communities scattered across billions of light years. The process begins in the spaces between galaxies, where primordial hydrogen gas, left over from the Big Bang, drifts through the cosmos at temperatures barely above absolute zero. This intergalactic medium contains roughly half of all normal matter in the universe, waiting to be harvested by hungry galaxies through their dark matter filament connections. Dark matter filaments act like cosmic conveyor belts, channeling this diffuse gas toward gravitational gathering points where galaxies form and evolve. The process resembles how tree roots extend through soil, gathering nutrients from wide areas and concentrating them where they're needed most. This steady supply of fresh material allows galaxies to continue forming new generations of stars for billions of years. The gas doesn't flow gently along these cosmic highways. As it moves toward galaxies, gravitational forces compress and accelerate it, heating the material through friction and gravitational interactions. Think of water flowing down a mountainside, starting as a gentle stream but gaining speed and turbulence as it approaches the valley below. This heating process creates observable signatures that astronomers use to trace the flow of cosmic nutrition. Gas heated to millions of degrees emits X-rays, creating faint but detectable trails that reveal the pathways along which galaxies receive their sustenance. The feeding process varies dramatically depending on a galaxy's environment within the cosmic web. Galaxies located at major filament intersections, where multiple cosmic highways converge, receive abundant supplies of fresh gas and tend to be larger, more massive, and more actively forming stars. These cosmic metropolitan areas bustle with activity and growth fueled by their excellent connectivity to the cosmic supply network. In contrast, galaxies dwelling in cosmic voids, far from major filaments, experience cosmic starvation. These isolated island galaxies must survive primarily on their initial gas reservoirs, like desert settlements cut off from major trade routes. They typically show signs of reduced star formation and may eventually exhaust their fuel supplies. The cosmic web's influence extends beyond simply supplying raw materials. The direction from which gas approaches a galaxy affects its rotation, structure, and ultimate evolution. Gas flowing along filaments tends to approach galaxies from preferred directions, creating the spinning disk structures we observe in spiral galaxies like our Milky Way. Recent observations have revealed the intricate details of this cosmic feeding process. Advanced telescopes can now detect the faint signatures of gas flowing along filaments, showing how galaxies actively draw material from their cosmic web connections. Some galaxies experience feeding frenzies when multiple filaments converge, delivering massive amounts of fresh gas simultaneously. These cosmic banquets can trigger bursts of intense star formation, creating the brilliant starburst galaxies that astronomers observe throughout the universe. At the grandest scales of cosmic architecture, filaments don't simply stretch endlessly through space, but converge at magnificent intersections where the universe's largest gravitationally bound structures take shape. These cosmic crossroads, where multiple dark matter highways meet, create the galaxy clusters that serve as the universe's greatest cities, bustling metropolitan centers where thousands of galaxies gather in gravitational harmony. Picture the intersection of major interstate highways during rush hour, but instead of cars, imagine entire galaxies flowing toward a common destination. These clusters, and the elongated chains of galaxies called filaments which connect them, form a highly complex and anisotropic matter distribution at the megaparsec scale called the cosmic web. These intersections represent the most massive structures in the universe, some containing the equivalent mass of millions of billions of suns concentrated in regions spanning several million light years. The formation of these cosmic intersections follows predictable patterns established by the underlying dark matter distribution. Computer simulations show that nodes naturally develop where multiple filaments meet, much like how cities historically grew at river confluences or mountain pass intersections. The gravitational pull of these developing nodes attracts more matter along the connecting filaments, creating a positive feedback loop that grows increasingly massive structures over cosmic time. As we approach one of these intersections in our imagination, the view transforms dramatically. What began as a journey along relatively sparse filaments suddenly opens into a cosmic megalopolis teeming with galactic activity. Instead of the occasional galaxy encountered along isolated filament stretches, cluster cores contain galaxy densities hundreds of times higher than average cosmic density. The night sky from a planet within such a cluster would blaze with the combined light of thousands of neighboring galaxies, creating perpetual cosmic dawn. The environment within these intersections profoundly affects galaxy evolution. Galaxies entering cluster cores experience gravitational interactions with their numerous neighbors, distorting their shapes and sometimes triggering intense bursts of star formation through close encounters. Think of how traffic patterns change when multiple highway lanes merge into a busy intersection, with vehicles forced into closer proximity and more complex interactions. Cluster cores also contain another remarkable feature: vast clouds of extremely hot gas that fill the space between member galaxies. This intracluster medium, heated to temperatures exceeding 100 million degrees Celsius, emits intense X-ray radiation that makes galaxy clusters among the most luminous X-ray sources in the universe. The gas represents material that has been stripped from member galaxies through gravitational interactions and heated through the cluster's immense gravitational well. The hot intracluster gas creates a hostile environment for star formation in member galaxies. As galaxies move through this superhot medium, the pressure strips away their own cooler gas reserves, like strong cosmic winds removing fuel supplies. This process, called ram pressure stripping, transforms gas-rich spiral galaxies into gas-poor elliptical galaxies over hundreds of millions of years, fundamentally altering their ability to form new stars. Despite the harsh cluster environment, these intersections play crucial roles in cosmic evolution. They serve as laboratories where astronomers can study galaxy interactions, dark matter distribution, and the large-scale structure formation process. The extreme conditions found in cluster cores don't exist anywhere else in the universe, making them natural experiments in extreme cosmic physics. Navigation through these cosmic intersections requires understanding their complex gravitational landscapes. Unlike the relatively straightforward gravitational fields along isolated filaments, cluster cores present chaotic gravitational environments where multiple massive galaxies, dark matter concentrations, and gas clouds all contribute to the total gravitational field. This complexity creates fascinating phenomena like gravitational arcs, where the cluster's combined mass bends light from background galaxies into spectacular curved streaks across the cosmic landscape. Some of the universe's most massive galaxy clusters sit at intersections where 6 or more major filaments converge, creating structures so massive they can bend spacetime significantly. These supercluster nodes represent the largest gravitationally bound objects in existence, with masses equivalent to millions of billions of stars concentrated in relatively compact cosmic volumes. The ongoing accretion of matter along filaments ensures that these intersections continue growing throughout cosmic time. Fresh galaxies arrive regularly along the various highways, while streams of intergalactic gas flow toward cluster cores, maintaining these cosmic cities as dynamic, evolving structures rather than static cosmic monuments. As we navigate through these bustling cosmic intersections tonight, we witness the universe's capacity for organization and growth, where the meeting of invisible highways creates visible monuments to gravitational architecture that will endure for cosmic ages. Between the bustling highways of cosmic filaments lie vast territories of almost unimaginable emptiness, the cosmic voids. These immense regions, stretching hundreds of millions of light years across, contain so little matter that a traveler could journey for cosmic ages without encountering a single galaxy. Tonight we drift into these serene cosmic deserts, where the universe reveals its most peaceful and mysterious face. To appreciate the scale of cosmic voids, imagine our local group of galaxies, which includes the Milky Way, Andromeda, and dozens of smaller companions, as a small pebble. A typical cosmic void would be an empty auditorium large enough to hold millions of such pebbles, yet containing only a handful scattered across its vast volume. These filaments and sheets are separated by cosmic voids, vast empty regions that challenge our understanding of how matter organizes itself on the largest scales. The formation of cosmic voids follows naturally from the same processes that create filaments and clusters. In the early universe, regions that started with slightly lower than average density continued to lose matter as cosmic expansion and gravitational attraction drew material toward denser neighboring regions. Over billions of years, this process carved out enormous cavities in the cosmic web, like soap bubbles forming in cosmic foam, each bubble representing a region where matter has been systematically drained away. The emptiness of cosmic voids is almost beyond human comprehension. While the average density of matter in the universe equals roughly 6 protons per cubic meter, the interiors of cosmic voids contain matter densities 1/10 that value or less. To put this in perspective, the best laboratory vacuums on Earth contain trillions of times more particles per unit volume than the emptiest regions of cosmic voids. Yet cosmic voids aren't entirely empty. Careful observations have revealed sparse populations of void galaxies, isolated island universes that formed in these cosmic deserts despite the challenging low-density environment. These void galaxies tend to be smaller, less massive, and more actively forming stars than their counterparts along filaments and in clusters. They represent cosmic pioneers that managed to gather enough material to form galaxies despite their disadvantageous positions in the cosmic web. The few galaxies that do inhabit cosmic voids experience remarkably different evolutionary paths. Without the steady streams of fresh gas that filament-connected galaxies enjoy, void galaxies must rely primarily on their initial material endowments. However, they also avoid the disruptive galaxy interactions and gas stripping processes common in denser environments, allowing them to evolve in relative isolation like cosmic hermits pursuing independent destinies. Void galaxies often display unusual properties that reveal the importance of environment in galaxy evolution. They tend to be bluer than average, indicating active star formation fueled by undisturbed gas reservoirs. They also show less evidence of past galaxy mergers and interactions, preserving more pristine records of how galaxies form and evolve in undisturbed conditions. The boundaries of cosmic voids aren't sharp walls but gradual transitions where density slowly increases toward the surrounding filaments. These void walls, as astronomers call them, contain elongated chains of galaxies that mark the transition zones between void interiors and the denser filament networks. Think of these boundary regions like coastal areas where ocean meets land, creating unique environments that combine characteristics of both domains. Recent discoveries have revealed that cosmic voids possess their own internal structure. Rather than being perfectly spherical empty bubbles, large voids often contain internal subvoids and connecting tunnels that create complex three-dimensional geometries. Some researchers describe this structure as resembling Swiss cheese, with holes of various sizes connected by tunnels and chambers throughout the cosmic volume. The expansion of the universe affects cosmic voids differently than denser regions. While gravity works to slow expansion in areas where galaxies and dark matter concentrate, cosmic voids experience less gravitational braking and expand faster than the overall cosmic average. This differential expansion gradually makes voids larger and emptier over cosmic time, enhancing the contrast between the densest and most sparse regions of the cosmic web. Cosmic voids also provide unique laboratories for testing theories of gravity and dark energy. The behavior of matter and spacetime in these low-density environments can reveal subtle effects that are masked by stronger gravitational influences in denser regions. Some theories predict that modifications to gravity or dark energy properties would be most readily detectable in void environments. As we drift through these cosmic deserts tonight, we experience the universe's capacity for both organization and emptiness, where the absence of matter creates spaces as magnificent and mysterious as the most densely packed galaxy clusters. Our final destination on tonight's journey brings us home to examine our own cosmic neighborhood and the Milky Way's place within the grand architecture we've been exploring. Far from being cosmic wanderers adrift in empty space, our galaxy and its companions occupy a specific address within the cosmic web, connected to the universe's largest structures through the same dark matter filaments that guide galactic evolution throughout the cosmos. The Milky Way resides within what astronomers call the local sheet, a relatively flat distribution of galaxies that forms part of a larger structure called the local supercluster. Our cosmic neighborhood includes the nearby Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller companion galaxies, all gravitationally bound together in what we call the local group. This family of galaxies occupies a region about 10 million light-years across, a modest cosmic suburb compared to the massive galaxy clusters we encountered earlier. But our local group doesn't exist in isolation. We're connected to the broader cosmic web through filamentary structures that stretch toward the Virgo cluster, a massive galaxy cluster containing over 1,300 member galaxies located about 54 million light-years away. Think of the Virgo cluster as our cosmic downtown, a major metropolitan center connected to our suburban neighborhood through cosmic highways of dark matter and sparse galaxy chains. Recent three-dimensional maps of our cosmic vicinity reveal that we occupy a relatively quiet region of the cosmic web. The local group sits near the edge of what's called the local void, a cosmic desert stretching about 150 million light-years across. This positioning explains some characteristics of our galactic neighborhood. We don't experience the intense galaxy interactions common in cluster cores, but we also don't receive the abundant fresh gas supplies that fuel star formation in galaxies along major cosmic filaments. Our location within this cosmic geography has profoundly influenced the Milky Way's evolution and our existence as conscious observers. The relatively peaceful environment has allowed our galaxy to maintain its spiral structure and continue steady star formation for billions of years. Had we formed in a dense cluster core, gravitational interactions might have disrupted our galaxy's delicate spiral arms and stripped away the gas needed for ongoing star formation, potentially preventing the formation of solar systems like our own. The dark matter halo surrounding the Milky Way connects us to larger cosmic web structures through what astronomers call the cosmic web's feeding filaments. These connections continue supplying our galaxy with small amounts of fresh intergalactic gas, maintaining the fuel supply needed for new star formation. Recent observations using radio telescopes have detected streams of hydrogen gas flowing toward our galaxy along these cosmic pathways, confirming that the Milky Way remains actively connected to the cosmic web's supply network. Our position also affects the night sky we observe from Earth. Because we sit relatively close to the local void, we see fewer bright galaxies in certain directions compared to others. The famous Virgo cluster, visible to telescopes in the constellation Virgo, represents our view toward one of the cosmic web's major nodes. In contrast, looking toward the local void reveals far fewer bright galaxies, creating the impression of empty cosmic desert in those directions. The cosmic web's influence extends to our galaxy's satellite companions. The large and small Magellanic Clouds, visible to southern hemisphere observers as fuzzy patches in the night sky, are small galaxies currently falling into the Milky Way along paths determined by the local dark matter distribution. Their orbits and ultimate fate reflect the gravitational environment created by our position within the cosmic web. Looking toward our cosmic future, the cosmic web will continue shaping our galactic destiny. In approximately 4.5 billion years, the Andromeda Galaxy will collide and merge with the Milky Way, an event orchestrated by the gravitational forces operating within our local group. This cosmic collision, which astronomers have dubbed Andromeda, represents our participation in the ongoing evolution of cosmic web structures. Our journey tonight has taken us from the universe's largest structures down to our own cosmic backyard, revealing how we're intimately connected to the cosmos through invisible threads of dark matter that stretch across billions of light years. The same physical processes that create massive galaxy clusters and cosmic voids also determine our galaxy's characteristics and our existence as observers contemplating the cosmic web's magnificent architecture. From our small planet orbiting an ordinary star in an unremarkable spiral arm, we've discovered our place within the universe's grandest structures, finding that even in cosmic terms, we truly belong to a connected, organized, and wondrous cosmic community. And on that note, our peaceful journey through the cosmic web draws to a close. Tonight we've drifted along invisible highways of dark matter that stretch across billions of light years, connecting every galaxy in existence through a magnificent network that rivals the most complex structures found anywhere in nature. We've witnessed how these ethereal filaments channel the raw materials for star formation, creating cosmic rivers that nourish galactic communities throughout the universe. We've navigated through the bustling intersections where cosmic highways converge into the universe's greatest cities, explored the serene emptiness of cosmic voids, and discovered our own place within this grand architecture. The cosmic web reveals a universe that, despite its apparent chaos, possesses an underlying order and connectivity that links the smallest quantum fluctuations to the largest structures we can observe. Thank you for joining me on this tranquil expedition through the cosmos. Until next time, keep gazing upward and wondering at the invisible threads that connect us all to the stars.